We have so far been looking at the idea of angular velocity for an object that is going around in a circle. Now I'm going to look at a situation where an object is going in a circle and we are interested in its linear velocity. What is linear velocity? It is the usual velocity that you already know. First we will talk about linear speed, then we will talk about linear velocity. Now what is speed? Speed, I'm using the symbol SP, but generally we can also call it V without the vector. Speed is distance by time, right? But this is not really speed, this should be called average speed. But right now, since we are talking about uniform speed, we will think of it as distance by time. Okay, now suppose the particle starts here and has an angular velocity of omega, and so it goes from here to there, right? If this was radius r, the question is, in time t seconds, how much angle would it have covered? So let me call it delta theta. So what is delta theta? It is omega times t, right? So this is the angle that it has moved through. But if this is the angle, usually we would have called it theta, I'm calling it delta theta. Okay, if this is delta theta, then what is the arc length? What is S? S, the arc length, it's not displacement, it's arc length. How much is it? It is r times angle. Angle now is delta theta, so it is r times delta theta, which is r times omega t. So what is S by t? S right now is actually the distance traveled by this particle. The particle travels along the circle, so it has traveled a distance of S. So this is actually distance, not displacement, distance by time. How much is that? R omega, because S is r omega t, so S by t is r omega. But what should this be called? This should be called the speed. I'll use the symbol SP, okay, so or V, which is equal to r omega. So we write V equals r omega. Now this was for the uniform case, right? If it is moving at a uniform rate, it would have covered an angle of omega t. So because this delta theta would be omega t, and so it would have had a arc length, so that means the distance that is covered is also equal to r times omega t. So therefore we can say that S by t is equal to r omega, or the speed is equal to r omega. But suppose it was not uniform. Will the formula change? Let us think. So suppose I said I started here, instead of starting there, now I'm saying I'm starting here, and I'm going to move by a very small angle. So this angle I will call it d theta. Instead of delta theta, now I'm going to call it d theta. What is d theta? It should be omega dt, because omega is changing. This is omega at this instant. So this is where the object is at t. This is t plus dt. Okay, so how much time interval has it traveled for? Dt seconds. So in dt seconds, how much angle would it have covered? Omega dt. What would be the arc length it would have moved? I'll call it ds. Now ds must be equal to r times d theta. Correct? Because the angle that you have turned by is only small, it's d theta. So r times theta, theta here is d theta. But what is d theta? Omega dt. So I get r omega dt. So what is ds by dt? Remember, S is not displacement, it's arc length. So this is actually d of distance by dt. We have not usually used this idea, but d of distance means how much are you moving? Distance moved by time. This should be called speed. Okay, so I'll basically write it as instantaneous speed. Now, instantaneous speed is the same as the magnitude of instantaneous velocity, which is why we use this symbol. Keep this in mind. So speed instantaneous, speed is equal to magnitude of instantaneous velocity. That's why nobody uses a separate symbol for speed. But average speed is not equal to magnitude of average velocity. It is not equal to. Keep that in mind, because suppose I went around and came back, my average velocity is 0, magnitude of average velocity is 0, but my instantaneous speed is not 0. My average speed is not 0 because I've covered some distance in some time. Okay, so remember, average speed and this are very different, but instantaneous speed is actually just the magnitude of instantaneous velocity, because you don't have time to turn around, change. So this is a point that we should have learned from straight line motion. Okay, so when we are doing that, but right now let's not worry too much about this. This is the speed, instantaneous speed. Instantaneous speed is ds by dt. But ds by dt, ds I just found is r omega dt, so ds by dt is r omega. Now this is the non-uniform case. So whether it is uniform or non-uniform, this is valid, which means v equals r omega. Instantaneous v is equal to r omega always. Uniform, non-uniform doesn't matter. Basically, the arc length that you have moved is r times d theta, which is r times omega dt. So therefore, arc length divided by so that is the distance traveled divided by the time is r omega. That's what this says. Is that okay? Is this the velocity? No, this is the speed. This is the speed. Why am I insisting that this is speed and not velocity? Because at this point, the velocity is going to point like that. At this point, the velocity is going to be like that. At this point, the velocity is like this. Here, the velocity will be like that. At every place, the velocity is going to be tangential. Why? Because here, you're going to move along this circle. So if you took a tiny portion, look at it, you're basically moving along the tangent. So the velocity is always tangential to the circle. What does it mean it is tangential? It will be perpendicular to the radius vector. So velocity vector is always perpendicular to the radius vector if the object is moving in a circle. So I hope that is clear. How do we calculate the velocity? This gives me the speed, but how do I calculate the velocity? That is something that we need to think about carefully. So for example, if I was here and let us say my r was 10 meters and let us say the omega was let us say 2 radians per second, my velocity is 20 meters per second in this direction. So it is 20 meters per second this way. This I will call it j cap, right? That is I cap, this is j cap. But if I wait for some time and then this point, you're talking about this object's velocity. It has a velocity in this direction because it's moving like this. R omega is 20, so 20 meters per second. But now in this direction, that direction is minus I cap. So minus 20 I cap. Okay, so the velocity comes with a direction. When you look at this point, for example, the velocity is going to be in that direction. You need to find the velocity properly by using angles. Let us now look at this question. So in this question, the object is moving uniformly in a circular motion, right? So basically uniform circular motion. Now it could be uniform circular motion in this direction or in that direction, but it says in the anti-clockwise direction. So that means the object is going like that, anti-clockwise direction. The time period of, when you just say time period, what does it mean? It means one full revolution. So you know that the time period is 2 pi by omega. But you can also write this in a different way. You can say time period is 2 pi r by v. Why? Because v equals r omega. So if you substitute, you will find that it's the same thing. But you can also say that if I went round, how much distance would I have traveled? 2 pi r divided by v. So 2 pi r by v is the time period. So both are useful ways to think about time period. Okay. So since I've been told the time period is 4 seconds, I can directly write my speed is 2 pi r by the time period. So 2 pi into 10 divided by the time period of 4 seconds. So that is 5 pi meters per second. So that is our speed. Okay, this is one way to calculate it. So the linear speed of the particle at A is 5 pi meters per second. The linear velocity would be in this direction. But I'm only interested right now in linear speed, so it is 5 pi meters per second. So I hope that is clear. But I didn't use omega for this, but you could have done it. You could have said omega is 2 pi by t, so 2 pi by 4 or pi by 2 radians per second. And therefore the speed at A is r omega, r is 10, so 10 into pi by 2, which gives me 5 pi meters per second. This I'm using the formula r omega. Here I did not use the formula r omega. I instead said total distance traveled 2 pi r. But I know how much time it took. In fact, it went this way, right? So total distance traveled 2 pi r. How much time did it take? V. So therefore 2 pi r by v. But that's only possible if you knew this was moving with constant speed. Okay, this uniform circular motion means constant angular velocity. So this means one, constant angular velocity. Omega is a constant. You can also think of it as linear speed is a constant. So sometimes people write this as uniform speed circular motion. But we can also think of it as uniform angular velocity circular motion. Okay. Now, when you say uniform angular velocity, you're also talking about the sense in which it moves, and that's what people mean when they say uniform circular motion. You don't say constant speed, I'll go at the same speed, then I'll bounce back at the same speed. That is not called uniform circular motion. You also mean it must be constant speed and must be going in the same sense. So linear speed constant, right, is not good enough. I would like to think of it as constant angular velocity. Omega vector is a constant. Okay, but both are good definitions. So when you say uniform circular motion, speed is constant. So then we can say total distance 2 pi r by v gives me the time period. Okay, so that's fine. So that gives us the answer to this part of the question, right? What is the linear speed at b? Well, linear speed at b is also the same magnitude, but the velocity, linear velocity is going to point like that. So therefore, velocity vector at b, if I call that I cap, this is in the minus I cap direction. So it is minus 5 pi I cap meters per second. Is that okay? Now we want to talk about average acceleration. What is average acceleration? It is final velocity minus initial velocity as vectors divided by the time. This is actually v minus u by t, except remember that is not acceleration, that is average acceleration, because acceleration is not constant. Why is it not constant? Because the velocity is changing direction. Okay, when velocity is changing direction, acceleration will also change direction, so it won't be constant. So we are talking about the average acceleration. Average acceleration is this velocity minus that velocity. What is velocity at b? Velocity at b we already found, minus 5 pi I cap minus, what is the velocity at a? Well, it is 5 pi in the j cap direction. So 5 pi j cap divided by the time. How much time will it take to go from A to B? A and B are like this 90 degrees, right? How much time will it take to go from A to B? Well, it took totally 4 seconds. So this is going to be 1 second, 1 second, 1 second, and 1 second. How do I know that? Because it's uniform. Okay, so this is going to take 1 second. We can also do this by saying omega is pi by 2. The angle it has turned by is pi by 2. So pi by 2 by pi by 2, the time it's going to take is 1 second. So this is just simply 1 second. So many meters per second by second. So the average, right, this is the average acceleration vector, I'm not writing the vector, is minus 5 pi into I plus j meters per second square. So if you wanted the magnitude of the average, right, acceleration, by the way, when the word comes without any qualification, that is, you're saying average, but you're not saying linear, it means linear. If you wanted angular acceleration, which we will study next, you will have to say average angular acceleration. If nothing is said, it means linear. Okay, so what is the magnitude of this average acceleration? It is minus 5, of course, will just simply become 5 pi root of 1 plus 1, 1 square plus 1 square. So it will basically be 5 root 2 pi meters per second square. That would be the magnitude of the average acceleration. This is the average acceleration vector. I'm putting the vector symbol on top, but that's very confusing because with the average. Okay, but it's the average acceleration vector. We don't know whether we want the magnitude or the vector. So I'm assuming this is the vector and this is the magnitude. Okay, let us think about this. Minus 5 pi I plus j. I plus j will look like that. The acceleration looks like this. This is the acceleration direction. But makes sense, right? Because if somebody was going that way and you want to turn it this way, you have to pull it down. Okay, so if I had this as my initial velocity and this is my final velocity. If I want to turn it like this, I must be pulling it this way. And so that is the direction of the acceleration. So I hope this is clear. So with this, I hope you understand how to use V equals R omega to find the speed and then use the speed to calculate velocity. The velocity comes with a vector direction, right? So that means you must have an I cap, J cap type of component that you do. Of course, here it was very simple. This had only J cap, that had only I cap. Let us look at another example where you'll have both I cap and J cap. Let us look at this idea of linear velocity and linear speed by doing a small example. So here we have a particle that is going around in a circle in the anti-clockwise direction, that's already shown, with an omega which is angular velocity which is 5 radians per second. The circle's radius is 10 meters and we want to know what is going to be the velocity of the particle when it is at A. A makes an angle of 37 degrees. So first thing that we know is the velocity must be pointing like this. Why should it be pointing like that? Because omega is in this direction, right? Omega is in this direction, so the particle is moving like that. Always there is going to be a small confusion about tangential velocity because you can say that it can be in that direction, it can be in this direction. That is something that you must figure out from the sense of angular velocity. Is it going to be like this or is it going to be like that? If it is going to be like this, the velocity will be like that. If it is like this, the velocity will be like this. Please do remember, the velocity has to be perpendicular to the radius vector. So this angle is 90 degrees. This is the radius vector, that is the velocity. Okay. Now when the angle is 37 degrees, we want to find the linear speed and we also want to find the linear velocity. Linear speed is very easy. Sometimes if I don't write linear, I just write speed. What does it mean? Linear speed. But if I want to talk about angular speed, you must say angular velocity or angular speed. If you don't use the word angular, it does not mean angular. But linear, if you don't write, it means linear. Okay. So speed, what is the speed? Speed V is R omega. That is very easy. R is 10, omega is 5. Now 10 meters into radians per second. But meter into radians is just meter. So therefore this is 50 meters per second. So I know that the speed is 50 meters per second. So that is easy, right? I want to know what is the velocity vector basically. When I'm talking about the velocity, I want it with magnitude and direction. Well, it is 50 meters per second, but if I want to know what components it has with respect to I and j, I must draw this axis parallel to the x-axis. Now if this is 37 degrees, what is this? 37 degrees, because they are alternate angles, okay, on the two sides of the transversal. So that means this is 37 degrees. And so this angle is 90 minus 37 degrees, which is 53 degrees. And so if you took this velocity and looked at its component in this direction, how much will that be? That is going to be V cos 53. But cos 53 degrees, we know. How much is it? Sin 53 is 4 by 5, cos 53 is 3 by 5. So this is 3 by 5 into V. V is 50. So this is going to give me 30 meters per second in this direction. Okay, so if I want, that is my I cap direction. So therefore I will write Vx. Vx is minus 30. V's component is basically 30 in this direction, but you want it in that direction. So it is minus 30 I cap. That's not over, right? That only helps me find this component. I also need the vertical component. The vertical component is V sine 53 degrees, and that will be the component like this. So it is in the j cap direction. Sine 53 is how much? 4 by 5. So 4 by 5 into V. V is how much? 50. So this is going to give me 40 meters per second. Upwards, which is plus 40 j cap meters per second. So this is how you will convert from speed to velocity with its vector components. Very, very important. The velocity components here very different from the velocity components there. It is also something that you should keep in mind. If the object was going around like that, then that means its velocity will be pointing that way. So it will have a component x which will be positive, but it will have a negative component for the j. I cap will be positive, the j cap component will be negative because it will be pointing downwards. So it does matter whether the omega is this way or omega is that way. And of course, where exactly you are also matters when you're calculating velocity. So in this question, we have been given theta. Okay, there is a particle that is going around in a circle, but we have been given theta as a function of time. And we want to find the particle's linear velocity, not speed. Velocity at t equals 0 and velocity at t equals 2 seconds. First, let us calculate at t equals 0, what is the theta? If I put t equals 0, I get pi by 3. What is pi by 3? 60 degrees. So the particle is here, where it is pi by 3, which is equal to 60 degrees. So this is where the particle is at in the beginning. What happens at 2 seconds? What is so special about 2 seconds? Well, if I try to put in 2 seconds here, I am going to get theta is pi by 3 plus 4 into 2 minus 2 cube. You see that 8 minus 8 will cancel out. So it's back where it started. It's back where it started. Okay, so the particle probably went like that, and then maybe somewhere there turned around and came back. So initially I expect its angular velocity to be in that direction. Finally it's coming back, so I'm expecting it to be in this direction. So I expect initial velocity to be like that, and I expect the final, that is at 2 seconds, the velocity to be pointing that way. It is back where it started. Look at this, pi by 3, pi by 3. So how do I find the angular velocity? Well, that is no big deal. It is just simply d theta by dt. I know theta is this expression. Notice that at t equals 0, it's not starting at the x-axis. It's starting somewhere there, which is okay. It can start anywhere where it wants. So d theta by dt, but this, when I differentiate, that is going to give me 0. So the starting point does not matter for angular displacement. Therefore, it does not matter for angular velocity. It matters for angular position. It doesn't matter for angular displacement and velocity. So anyway, the d theta by dt, this part will go away. And the second one is going to be 4t differentiated is 4 minus 3t square radians per second. Clear? This is the angular velocity at any time. What is the angular velocity at time t equals 0? Well, that is 4 radians per second. Notice it is positive. Okay, so that means it is going in this direction. Since it's going in this direction, you expect the velocity to be pointing like that. How much is the speed? Speed must be r omega. R is 4, so 4 into 4, 16 meters per second. Like that. Making an angle of 60 degrees. Notice that if this is 60, this must be 60, that must be 30 degrees. So 16 cos 30. So the velocity at time t equals 0, I'll call it V0. Okay, what is the velocity? It has 16 cos 30 this way. So 16 cos 30 degrees. But it's pointing in this direction, that is the I cap direction. So that means I must put minus and I must say I cap. Plus, is there a j cap? Yes, 16 cos 30 and that is 16 sin 30. So 16 sin 30 degrees. And that is in the upward direction, so it is plus j cap. So if I calculate cos 30 is root 3 by 2. So if I divide the by 2 out, it is going to be minus 8 root 3 I cap. Sin 30 is just half, so plus 8 j cap meters per second. So this is the velocity at t equals 0. Okay, so that is the answer to the first part. But if I try to calculate what happens at 2 seconds, t equals 2 seconds, I need to substitute 2, right? So 4 minus 3 into 2 square. 2 square is 4, so this is 12. 4 minus 12 is minus 8 radians per second. Do not ignore the minus sign. What is the minus sign telling you? The object, when it is coming back, is going like this. It went like that and then it's coming back like this. So that means when I find what is the speed at 2 seconds and I say it is r omega, r is 4 meters into minus 8, it is going to give me the answer as minus 32. Don't do that. This is only the speed. So this is 32 meters per second. So when you're talking about r omega, v equals r omega, we are talking about magnitude of omega. This is only the speed. So the speed is 4 into 8, 32. First of all, it's different from the speed that was there, that was 16. This is now much faster. This is 32 meters per second. If instead of t cube I had a t square here, you would have noticed that basically this will also be 16. We will come back to that idea later. But at this point what I want you to see is that this is 32. It is t cube, so it is 32. 32 pointing like this. How do I know it's pointing like this? Because this is minus 8. Don't look at r omega, look at this. Omega is now in this direction. Since omega is in this direction, the velocity must be in that direction. You must always look at omega direction to find the speed. After that speed, you must basically use omega direction, not to find the speed. Speed is r omega. After that, to find velocity, you need to look at the direction of omega. So if omega is like this, the velocity is going to be that way. If omega is like this, the velocity is going to be that way. Okay, now I've got my velocity to be this way. What is the vector component for this, right? This is 60 degrees. This would be 60 degrees. This would be 30 degrees. So 32 cos 30. So velocity at time 2 is 32 cos 30 degrees. But notice it is in the I cap direction, plus I cap. And then 32 sin 30 degrees. Okay, so that is 32 sin 30 degrees. But it is pointing downwards. Because when I resolve this that way, I am resolving it like this. So this component is downwards. So 32 sin 30 is pointing downwards. So I will say minus and I will put a j cap. Now of course cos 30 is root 3 by 2. So if I take that, this is 16 root 3 I cap minus 16 because sin 30 is half. So 16 j cap meters per second. So notice something interesting. Different points of time. It's the same point in position, but different time instants, you have different omega values. So depending on the omega value, your velocity, the speed itself has changed because that is 16 and this is 32. But not just the fact that the speed is different, this is pointing that way and this is pointing this way. So if you look at the vector, this is not exactly the same as that, right? Because you see, this has a minus I cap, this has a plus I cap. That has a plus j cap, this has a minus j cap. And this is of course 8 root 3, this is 16 root 3. That we can see 16 meters per second, 32 meters per second. So it was double because the omega magnitude wise was double. So the speed was double. But it's not just the fact that the speed was double, it was in the opposite direction. So I hope it's clear how to calculate both the linear speed as well as the linear velocity from the angular velocity. If the question had told you that you had, let us say, 2 k cap radians per second as omega, then at this location the object is going this way, so the velocity will point like that. But at this location the velocity will point like this. At this location the velocity will point like that, everywhere perpendicular to the radius vector. But if I told you it was not plus 2, suppose I told you it was minus 2 k cap, which means it's now going this way. Why? Because plus 2 k cap will mean this, minus 2 k cap it will mean, because it's pointing like that, the arrow for angular velocity is that way, so that means the object is going like this. So then the very same situation, this guy is going to point like that, this is going to point like this is going to point like that. So v equals r omega only gives you the linear speed. The velocity calculation involves a little bit more, knowing which direction is omega, therefore what should be the tangential velocity direction, then doing some resolution to find out what should be the components of that velocity. The speed is given by the formula v equals r omega.